All right, so we come to the very last part of this course, and we got one last, say, technical part. The very last few equations, and then the last part would be just a bit of an overview of all the various applications where ISA takes place. Okay, so we'll see pictures and systems and stuff like that. So this is the very last sort of more technical part. And we mentioned before cross-range. Cross-range direction, that means across the range. Right? That particular direction there needs to be scaled if we want to form images that are fully scaled in special coordinates. To do that, as you know, we need to take care of one parameter that is not under our control and actually depends on what the time is doing. To summarize, scaling operations along the two coordinates, the two imaging coordinates, are the range scaling, which is simple. Once you have tau, the delay time, you just scale it by multiplying by c and divided by 2. That's basic. Doesn't require anything. For these other particular scaling, so from Doppler to cross range, well, that requires the knowledge of this guy here, which is the magnitude or the effective rotation vector. We've seen that. We know that this depends on what the target is doing, depends on the geometry, but also the dynamics. Okay? And nobody's going to give us this, so we have to find a way of estimating this term. So now we're going to go through a little bit of signal modeling and a little bit of signal processing to estimate this term here. And once we have an estimate of this term, we place it back into this equation here, and then we're able to transform Doppler frequencies into spatial coordinate, so from hertz to meters, pretty much. So here's the signal model that I'm referring to. So I've condensed the signal model into just looking at the phase of my received signal. Once I have removed the radial motion compensation term, R0t. So that's the phase that appears inside, okay, my integral. And that is the form that I took, right? And from there, if you remember, I defined those capital X1 and capital X2 as 2f divided by c times sine and times cosine. So now I want to do something different. I'm not going to go that path. I'm going to go a different path. And I'm going to say, all right, if this is the expression of my received signal for a given effective rotation vector, now I want to represent this phase with an approximated polynomial, and I want to stop at the second order. So what I want to do is, okay, take this expression at t equal to 0, and that's the 0. So this is 0, this is 1. So what I'm left with is just y to the k. And I take the first derivative, okay, and I select time t equal to 0 again, and the first derivative returns me this one. First derivative then becomes the cosine, then becomes the sine. So the sine in t equal to 0 is 0, so this term doesn't appear in the first order, but this term appears in the first order now, and it's omega f times yk times 2. If I take the second derivative, this again becomes a sine, and this becomes a minus cosine. So second derivative takes up 1/2 as well as this squared, because it's derived twice, and times t squared. So that's the second order term in this Taylor polynomial decomposition. Then I stop. Okay. Then I assume the other terms to be neglectable. So if I do that, and this should be an almost equal, right, this symbol, that becomes my phase signal model. So if I put this into my receive signal now, okay, and I take the Fourier transform, okay, from f to tau, so this becomes my receive signal as a function of range, or tau if you want, and slow time. As a function of tau, this becomes a sinc function, okay, and this term is my first term. So this is my, let's say, is to remind you of the steps I have to take to form an image. So I do radial, motion, compensation. So I call this as R on F at T. And that would be S R prime on F and T or that's not that prime. S compensated. Good. So the compensated signal, okay, usually what I do, I take an inverse two-dimensional Fourier transform, and here I obtain an image. What I'm doing here instead, I'm splitting this two-dimensional Fourier transform into two one-dimensional Fourier transform. Being this one from F to tau, and this one being from T to mu. Okay? I can always do that. I can always split the Fourier transform into two steps. So what I'm referring to there is this point here. This for me is the SR K of tau and T. K stands for the K scatterer. Now I'm considering my target as a composition of point light scatterers. So this one, okay, that for me is the generic case scatterer. So I'm looking at the signal, all right, that I will receive, and I will process all the way up to here if only one scatterer existed, and if it was this one here. Then, of course, I can write my full signal as a superposition of all these contributions. So the total signal as R of tau and T will be the sum from K that goes from 0 to, I don't know, capital K of S R K of tau and T, right? So I'm only considering one component of that signal. And why am I considering one component? Because I want to study what's happening for every single component. And that particular scatterer there is got these coordinates y1 and y2. K stands for the K scatterer. And y1 and y2 are the two coordinates. One is y2 is the range, y1 is the cross range. Okay, so as you can see here, you got an expression, right, that depends, of course, on the system parameters. So the sinc function here tells you that if you get a wide bandwidth, you get a very narrow sinc, fine. And this is a phase term, right, that is associated with the motion of that scatterer. So that scatterer sits in a certain point because of the rotation effect. It will generate this phase term it changes in time. So this phase term here is not just linear, see? It's got also a quadratic term. So now this type of signal is some sort of chirp signal. It's got like a Doppler that is related to this t, but it's also got this Doppler acceleration, right, that depends on this guy here. And everything is constrained to be happening within minus t ops divided by 2 and t ops divided by 2. That's the duration of my signal. Okay? Good. What I'm looking at here. Well, if I want to match that type of signal, right? To match means if I want to match filter that type of signal now, I have to introduce an additional term that compensates for this. Linear terms, if I didn't have this, say this is 0, one way of matching this signal here, when I have constant Doppler, as we know, is a Fourier transform. Fourier transform provides a nice and quick way to match a filter all the possible Doppler frequencies that exist within a certain limit. Because Fourier transform is equivalent to creating a bank of narrow filters along the Doppler. So if I didn't have that, but now because I have this, now my matched filter cannot be a simple Fourier transform because I have to add another banks of filters for the quadratic term. And our way of doing that is to create a so-called polynomial Fourier transform. A polynomial Fourier transform means that now the kernel of my transformation is not just e to the minus j2 pi nu t. But now adding another term here that depends on this value m. M is called chirp rate. Because the higher or the larger, if you want, the value of m, the steeper is the chirp rate. So this is a chirp type of signal, right? The quadratic phase gives you chirp signal. So what happens now is that if this signal here that I'm receiving, which is called this expression here, it's got a certain phase here that it's got a certain Doppler at a certain Doppler acceleration, right? It will match this when this Doppler and this n are exactly equivalent to this value here and this value here. One will be with the sign, with the plus sign, the other one will be with the minus sign, and they compensate for each other. That means that all this phase disappears because it's cancelled by this term here. And what remains is just this value here, okay? Or just this sinc function here. So that means that a long time I add up coherently. So Fourier, if you want, finds that phase rotation, okay, and counteracts it. So that your phasor that is rotating because of this Doppler, right? And if you got a Doppler acceleration, it means it doesn't rotate with the same velocity, but it accelerates. Now, if you find the counter phasor, right, then you basically remove their rotation and your phasor stays constant. That's what Fourier does. And that's why you see a peak happening at that particular frequency. Does it make sense to you? Yeah. Been through that. So now, that means that there will be a particular value nu and a particular value of m that maximizes this. This function here, see, now is a function of 1, 2, 3 parameters. It's a cube. But it will have one maximum for a particular value of nu and a particular value of m. And this means that if I look at the maximum of this function over nu and over m, here, maximize this over nu and over m, I basically obtain these two values, which are the maximum values, which will be equivalent to these guys here. And why that? For the same reason I said before, because this phase will remove this phase, and you remove it if you estimate these two values here. These two have to be very close to this. So this becomes an estimator for the Doppler and the chirp rate. Right? So that means I can estimate both Doppler and chirp rate. Good. Let's look at this other side. If you look at M particularly, okay, M, see, depends on, okay, the frequency, depends on the range coordinate, and depends on the square value of the effective rotation vector. So that means the M is proportional to the range coordinate through this factor here that contains this guy multiplied by this guy here. So A for me is exactly that. Do you see? There's a linear relationship between the chirp rate and the range position. So that means if I have a scatterer, so the rate is down there, and I've got a scatterer here, right? And I have another scatterer. So the chirp rate of that scatterer here, okay, will be dictated by this relationship, and me too. I will generate another chirp, and because I'm further away, my chirp will be bigger than that. Not only will be bigger, but if this is halfway through between me and the radar, and I'm double the distance, my chirp rate will be double. It's a linear relationship. Okay? So that tells me the further you go, the higher the chirp rate. Fantastic. We've got a linear relationship. So now, if I am able to estimate this value of A, okay, then I'm able to estimate the effective rotation vector. And the effective rotation vector, in fact, will be the square value, okay, of this multiplied by the magnitude of A, or absolute value of A. This has to be positive all the time. It's a magnitude of a vector. It has to be positive. Good. And at this point, I have to estimate A. Right? If I get an estimation of A, I get an estimation of my omega. And that's what I want. If I get this, I can put it back here, and it's done. To get this, I have to get this. And this appears in here. Now, can I measure ranges? Range can be measured because a scatterer, right, is scaled. Its position in range is actually known. So I've got one scatterer here, one scatterer here, one scatterer here. The range positions of these scatterers is measurable. I can measure it. Take my image, pick up bright points, and I look. The range scale is actually correct. The Doppler doesn't tell me where they are along the cross range, but the range is fixed. So that means that for each scatterer that I can see, I can measure, I have for the scatterer the chirp rate through this, and the range through the position. So now it's a matter of identifying these points, right? And you can do it in many ways. One way of doing it is by segmenting this image into dots, right? Or you can even do it manually, but if you want somebody to do it automatically, then you have to find a way of extracting peaks. Once you've extracted peaks, right, then you basically isolate that scatterer from the rest of the image. And what you do, you run this, okay, you calculate this polynomial Fourier transform locally as the area. So you calculate local polynomial Fourier transform for each of these components. It's like you're filtering them out in this domain, the image domain. Good. So if you do that, and you segment your image in a number of sub-images, each of those contains one of these things. Well, if you do that, and you measure the chirp rate, your estimated chirp rate, and you measure the range for each of those, what you obtain is a cloud of points. And these cloud of points, see, are defined in the range and chirp rate domain. Now, what's A? A should tell me that these are linearly related. And they're not perfectly aligned, okay, along this straight line. But this straight line, okay, is the least square error regression line that you can calculate, minimizing the distance between these points and this line here. So this should be, if I estimated things correctly, this should be the slope should be exactly related to this value of A. If things were perfect, these points would be all aligned here, and this would be a description exactly of this linear function here. You see? So what you obtain by estimating this regression line is get an estimation of that rule, and therefore an estimation of A. So once you've estimated A here, well, then you basically solve your problem. So let's have a look at it from a sort of a functional block scheme perspective. So again, my signal, motion compensation, as I said before, I do a first one-dimensional F15, and then I'm in this point here, right? Then I do, sorry, that's already two-dimensional, sorry, I'm already there. So I get my image, I segment my image, this. And for each segmented image, I calculate a centroid, because at this point, sorry, each of these will have a centroid, and I can calculate this centroid. I don't have to be exact, huh? As long as I don't pick up centroid of this down here, right? It's inside in here, it won't give me that much error. So these centroids are measurements of the range, this Y2K. So I get 1 for each scatterer. Say I got n extracted scatterers out of them. On this other end, for each segmented image, I basically let's forget about this for a moment. I can go through the whole full details, but what you do basically, you go through a chirp rate estimation by using the local polynomial Fourier transform, and you come out with estimations of the chirp rate, 1 per scatter that you have extracted. So these are labeled. So 1 goes with 1, 2 goes with 2, 3 goes with 3. So then now you build up these clouds of points, and then you go and estimate this regression line. Regression line estimation is a simple least square error. You have a closed form solution to solve that. So you don't have to do it iteratively or anything. Even MATLAB, you can implement it easily. But that's the formula anyway that you can derive for a least square error. So what you do, you get at this point an estimation of the effective rotation vector. It is a little bit complicated, I agree, but nobody else is going to give you the effective rotation vector. And if nobody gives it to you, that means you can't cross-range scale your image. It comes at the price of understanding it and implementing it. Once you've done it, you got it. Okay? Then you run every image you create, you run it through this process here, and automatically you get instances. So it takes some effort to derive it and implement it, but then it's done. Some examples, okay? Here is target. The data that I'm going to run here is real data collected, by looking at this target here. It's one of the previous radars that you've seen. this is the image segmentation. If you remember those images, okay, you can see it here. They got quite distinct scatterers there. So you isolate those, and you run, for each of those little sub-images, you run this search to find the chirp rate. So the chirp rate attempts to focus each of those, counteracting also the quadratic. Okay. So it does something more than Fourier, right? And look at here, see how they closely follow. This is better than the one before. Reason being that the signal to noise, let's say, ratio in this image is pretty strong. These are very bright spots. And when you get bright spots like those, then the algorithm works really well. And you can tell. So, and you can even be more confident out of this estimation than you were out of this one. So you can actually even give out some sort of the estimation confidence level that can tell you, look, this cross-ranging scaling here, believe me, it's done right. These are the one, a little bit less. It's important because then whoever makes a decision based on this, right, believe me, that person would like to know if your estimation is good or not. Because if you have to launch a missile at the house and destroy it, you want to make sure that's the enemy and it's not a civil, passenger boat. That piece of information, how confident you are with that, is very important. So when you come out with an estimation algorithm that also outputs some sort of confidence measure of your estimation, that's really good. If you can come up with something that can do that, so it's better. Thanks. So now I have cross-range scaled this image, right? From range Doppler, now it's range and cross-range, based on the estimation of the effective rotation rate. Now I can measure the distance between this point and this point, and measure the length of this shape. Couldn't do it before, now I can. And for the aircraft, that was the same data pattern before, for this aircraft here. Again, same passages, image segmentation, chirp rate, and centroid estimations. These points correspond to this. And that's the image, range and cross range. Now you can measure the fuselage length, so from the nose down to the tail. And you can measure half the wingspan, which means measuring the wingspan. And then you compare, right? So this was a Boeing 737, and the actual length, right? There's a family of 737s. They don't all have the same length. Unfortunately, we didn't know what chicken and motor that was. So we know that it ranges between 31 and 36. And we estimated 36.8 out of it. The actual wingspan is 28.88, and we measured 28.37. Well, I'm cheating here because the wing is along the range. Mostly. It's a little bit of angle, it's still tricky, but mostly it's along the range, and the range is accurate. Right? C over 2 is not accurate. Unless you're messing up with the speed of light. But I guess that's not the case. And the ball carrier, we measure 144, but ball carrier is like, we didn't know what that was really. I don't know how long that is. Ball carriers range from 150 to 170, so I don't know. That doesn't compare. But this is a good comparison because 0.737, roughly 100 there. So, you can do things like this, not only like other features that are important, for example, to classify aircraft. It's not just these two measurements here. It's also the distance between the nose and the point where the wing attaches to the fuselage. That may change. That can give you more clues about what type of airplane that is. Of course, you need a database of features to compare against if you want to classify or you want to recognize at that time. Classification is fine. Recognition is a level up. Recognition means you need a database of numbers. Classification could be, oh, this is a civilian airplane or military. That's classification. Recognition is okay. That's MIG, you know. All right, let's. This is finished. Okay, so mathematics done. Hoorah. Let's have a sort of a lighter presentation of ISA applications. This is I walk through a number of different types of applications where you might find ISA become useful because of the scenario. First of all, we all know classic radar mounted on the ground, looking at an aircraft, right? You can get an image. Now you know why you can get an image. You know how to get an image. You also know how to scale it if you want. This is not scaled, but you can do it. I showed you before. Ground-based, looking at space objects. And I've told you a few stories about this radar and these images, some very interesting too. From airborne systems, looking down at ships, and you get your ISA image through ISA processing. From space, and that's another interesting feature. From 700-800 kilometers, being able to form an image with 1 meter by 1 meter resolution through clouds at night. Well, that's where when radar defeats optical systems. Right, I want to tell you something more about this spaceborne ISA or maritime targets, because the way we implemented it is a bit particular, right? We don't have up there an ISA system that works, is designed to work as an ISA system. We've got a SAR system. SAR system is able to form images of targets that are moving on the ground, but the SAR processor, unfortunately, is not suited to focus those targets. It only focuses whatever is stationary. We understood that. So how can we now take the same product, which is a SAR image, and transform it into a better product where the stationary objects remain focused, but the moving targets get focused as well, and replace the defocus. You see my point? So you're basically trying to create an add-on signal processing that you attach to the output of the system and create something that is enhanced and improved. This has got two benefits. One, of course, is the final product is a better product. Two, very important, you're not changing anything of the system. Because changing a system like that will cost you a fortune. So you don't want to change anything. Just want to add on things so that you get better products without changing anything. So the idea was to create some signal processing that is able to take a SAR image as input. So a product, a standard product, SAR image standard product, take it as your input and produce something new at the output. So the idea is to get an image, detect targets inside an image, moving targets especially. For each of these moving targets, create some sort of a sub-image selection. So create some sort of crop function that selects all these targets. And then in parallel, starts a number of threads for each of those. So these targets that are selected would appear defocused. And you got a number of them. So you take this target, all right, and you go through what I call sub-image, okay, inversion. So what you're creating here, so the passage from here to here is still an image. The passage from here to here has to be something that produces what you would call a suitable input for an ISA processor. So what I'm doing here is the ISA processor that is here is what you come to learn. I don't want to change this either. So I got it, it's nicely tuned, works perfectly. I don't want to change a thing here. So I have to prepare the data from here to here. I have to to something so that the data is, right, can go through my ASA processor. And you know that to form an image, okay, you start from the signal model that is defined in F and T, right? And you form an image, which is an image displayed in spatial coordinates. But then you can go back, because you use a Fourier transform somehow, you can go back from what is an image back to the data using a Fourier inverse transform. And this passage here is harmless because Fourier, right, it can go back and forth a million times, nothing changes. Right? It's a bijective transformation. If you take it twice, go back to where you were. Transform, inverse transform, you go back. So it's what happens here. The data that you have here, it's a particular data because now this is not the same as you had before you formed the image. Because by selecting only that target, you filter out all the other targets, all the rest of the stationary targets that you call clutter or whatever, and you're only focusing on that particular target there. It's almost like from space, you had a beam that only collected the data from that target. So the data here is almost like it's that type of data. You see? So you're going through this filtering approach here. You filter each target separately. And then you're recreating the data that you would have collected if you had a very fine beam and you were looking just at those targets separately. And you can do this in parallel. So now if you feed your ASA processor with that data, well, that data contains the same information that it would have contained if you enumerated the target. And that information there contains the information related to the motion of that target that the sub-processor hasn't removed. So the residual motion of the target with respect to the point where the target, the sub-processor compensated for, the sentencing, for example. So any relative motion of this target hasn't been taken into account by this sub-processor. So that means that it's still in here. It's still in that phase. But now you can take care of it. And if you remove it and form another image via an FFT, then you should get a refocused version of your target. Simple, isn't it? Very simple concept. So what are we doing here? In terms of ASA processing, we do exactly the same, right? This should be here, this should be there. I don't know why it's so. But what we're doing is we're going through, the time window, autofocus, image formation, cross-range scanning, and we get our image. So to make you understand how we go from cross-range and range to slow time and frequency, right? So to go from here to here, we have to assume somehow that we know which algorithm has been used to form this image here. Because then we can invert it. And in truth, we can invert it there based on the algorithm that has been used, right? Polar format, omega k, whatever, we can invert it. Right? There's not all the details here. So what I'm showing here is the Fourier inversion, right? So the Fourier inversion, you go from cross-range to range, right? Range can be transformed into delay time. You go back, see? The scaling, you go back from cross-range to Doppler. So that's delay time and Doppler. So if you perform a two-dimensional FFT, then you get your data in slow time and frequency. So slow time is the Fourier transform of Doppler, and frequency is Fourier transform of delay time. So that's your data in the frequency and time domain that you're ready to feed into your ASA processor. You can even invert omega k, for example, and that's the way you do invert it. You can invert a chirp scan, you can invert a number of whatever you want. They're all inverted. Anyway, so once you get this data ready, slow time and frequency, you feed your ASA processor and you get your range and cross range focused image. Let's see a couple of examples here. So these are two images. One, this is in Italy. This is Sicily. And these are two ships here. There's another couple of ships we selected here. Istanbul, Turkey. And these are the images as they appear in the SAR image, right? You can tell they're defocused. All of them in their own way, they're not really focused. And you realize that these are not focused when you try and focus with an ISA processor. And you see the difference. So ship 1, 2, 3, and 4. See, this is the original one. And this is the one that we obtained by inverting using Fourier inversion. Just simple two-dimensional FFT. See the difference? Maybe we should turn the light. So you get this just with signal processing. You don't do anything here. And this is done by using, because to obtain this image, this is a Cosmos Skynet image taken with Cosmos Skynet satellites. And they use omega k to form the image. So we can invert it using the inversion of omega k to go back from the image to the data domain. Right? But you can see that the results of the Fourier works even better. The reason is that inverting this omega k is not exact, because there's an interpolation that you make when you form the image. Okay? And there's also an interpolation that you use when you invert from the image back to the data. So twice this interpolation doesn't allow you to go back exactly to where you were. So for this reason, the Fourier actually works even better. So that's a simple Fourier inversion, two-dimensional FFT, and fed to an ISA processor, and that's what you obtain. You can see the difference. This is the other ship. Even in this case, you see the difference. Right? It's just processing, and it takes literally a couple of seconds maybe to do the whole thing. And from here to here, you can see this is not too bad, but when you see the other one, then you can see even these two layers, right? The actual deck, and this is the superstructure on top of the deck, which you can't see here. And from here, again, to here, and you can see these structures here, superstructure here, the bow of the ship. It's definitely a better product. Right? And this summarizes, most of the time, the Fourier works better than the omega k. Only in this case, it actually works better. That's the image contrast of those images. We use the image contrast to determine which one is there. But even visually, you kind of see that only the last one here, this might be better than that. But in the other cases, this looks better than that. Slightly, but differences are small. Okay, this is faster though, because it doesn't need an interpolation. This is a little bit slow. So if you can do it faster, it's even better. Time windowing. You can even implement time windowing here. How do you do that? Well, once you've gone back into the data domain, you can interpret that data the same way. This way here. So now what you're doing, by time windowing, you're selecting subapertures. Yeah. And this is because if a target, in the time that the SAR processing, or the SAR system acquired the data, it could be sometimes a spotlight and here a couple of seconds, 3 seconds, 4 seconds. Right? You notice that if you increase the intuition time for certain targets that are maybe moving too much, that's too much, right? So if you're trying to form an ISA image of certain targets that are maneuvering or they're oscillating, well, the result is that the ISA process doesn't do any better than the SAR, because it's trying to use the whole intuition time and it's too long. So basically, when you go back from your image to your data through that inversion, say there's a Fourier transform from here to here, then you got the slow time and frequency, right? And you start creating windows here, right? These are time windows. So you can do 1, 2, 3, 4. You can even overlap them, form a movie. You do what you want. Once you've got the data in this format, You can apply even that code that I gave you, that selects the time windows. You can do that. And then you feed your ASA processor, see, with all these time windows and create a movie. If you do it in a sequence, create a movie. And here's an example, right? This is the same image. Then you try and refocus there with eyes out using the whole iteration time and see this ship was clearly rotating or doing something, and the image projection plane changes. So there's no way that you can do better because this is. But if you apply time windows, you can see this ship 1, 2, 3, 4, 5, and you can see that it's actually rotating. See the inclination from here to here changes. So this is the sequence goes this way. So out of a defocused image, you get a set of images. They even tell you what the target is doing a little bit. You can do a little bit of analysis of the behavior of the target. Clearly, it's not cruising, it's probably maneuvering. That's very interesting. Let's look at the cross-range scaling. Look how well this cross-range scale. Looks like a simulated dial, doesn't it? One of those things you show at conferences, look how good I am. But this is real data. This is actually one of those ships here. And here is the example for this. This is the example for that. They all respond really nicely. But look at how bright those spots are. Signal to noise ratio here is incredible. These are 45 dBs, right, of dynamics, and you don't even see the clutter. So probably got nearly 50 dBs of signal to clutter ratio. It's huge. So with a signal strength like that, your estimator walks. So, and here, this is not exactly the same. You get a lot of strange effects here. These are probably antenna things or whatever. Anyway, you get funny effects here. It's not too bad. There you go. We got to the end, guys. Finished. All right. Classic words at the end. Only a few. First I want to say that I was pretty impressed with your attention and your questions. It's been one of the best classes I've had, and I really mean it. So thank you for.
Say that to all your classes.
They always improve. No, seriously, I've been telling this also to some people here in my report that. Yeah, seriously, and I hope you're not gonna fail me with the exam. Right.
We hope you're not going to fail us.
Fair enough. Fair enough. Good. Now, seriously, I hope you learned a few things. 1 week, all this amount of information, I know it's very hard. And I don't expect, of course, you to learn all the single details. But I hope that the concepts are there. I always make an effort to explain things from sort of a physical point of view and try and explain the math so that it makes sense, because I know the formulas are other things. So I hope I accomplished my mission, at least my part of the game. Now we got a few more things to finish off, which is got a list of assignments for you. We have to set up a few dates about when to have tutorials and also the date for the exam, which is important. And yes, question for you was like also, do you all use Skype, or is some of you forbidden to use Skype? Like if you work from company, sometimes you can use Skype. Okay, that's good. That makes it easier. So that's going to be the tool that we're going to use in the next few weeks to communicate, to have tutorials, to have discussions. I want to use those hours that we will have in the next few weeks to maybe go through sort of like exam-like type of problems, tutorials, but also talk to you one-to-one about the assignment if you have questions. That's not compulsory, but if you're progressing and you have trouble or you want to discuss some points, of course, we can do it. There will be 3 appointments, one every week, for 3 weeks, and then there will be the assignment deadline due probably 1 or 2 weeks later. And for the exam, I believe there will be after the assignment deadline, some point. We have to decide about that. Is Stephen gonna be here then later to discuss that, or it's just up to me and them, or we have to make sure that there's a room somewhere, or somebody has to sit here. I'm not gonna come down.
No, I'll be there
Yeah, you'll be there.
tutorial and stuff.
Okay.
Because for the if it's like a meeting for like a huge group, then we usually use this app called Adobe Meeting. So we send out a link on
You use Adobe.
yeah, Adobe.
Oh, that's fine then.
Yeah,
So we don't have to use Skype
I
then.
think it's easier to communicate through that because you can post upload like.
I think
files.
I've used that one. Now that I remember.
Yeah.
Now that I remember, I think I
But
used
if
it.
you want it one-on-one, then Skype works better.
Also, yeah, for the assignment things, yeah.
But then we can set up all the tutorials dates, and then on that date and time, then I'll set up everything on the 7th floor, and whoever can attend physically.
Because then you can have multiple connections, correct?
Yeah.
That one. Oh, okay, that's good. So people from Pretoria can connect. Okay, that's good. Any more questions? And what's the time now? It's okay. So I've got a couple of things. One is the list of assignments that I can show you here. Then I've uploaded onto the ruler. There's 4 assignments, and you can choose from. Okay, that's the 4, let's say, problems to solve. And I don't care which one you choose. You can all choose the same one. I don't care. It's entirely up to you. I try to make them all interesting. But if you want to choose the same one, I don't care. Actually, I might show you that straight away. Okay, let's have a look at the assignments. Do you want me to stop this? Or it's the same? Just leave it as it is. Okay. Okay. That's wrong. Okay. So, first assignment, let's have a look. They all have pretty much the same structure. Of course, they ask for different things. They cover different parts of the course. So this one concerns the high range resolution stuff. Basically, what this problem is about is to basically implement one of those pseudo-random binary sequence generators. Right? So what you have to do using MATLAB, implement this PRBS to create all possible maximum length PRBS, okay, with a given value of n, where n is the shift register size. Okay? Don't choose huge shift register size because then it might be too slow. Test. Generate a PRBS with low side lobe level. As you know, pseudo-random binary sequences, they're randomly generated. They have this behavior where the side lobe level, right, is of the order of a squared value of n, okay, where n is the length of the PRBS. But when you generate more than one, okay, then they have different silo levels. So that's a sort of an average behavior. So what this one says, okay, so use a generator to obtain n sequences. For example, 10, it can be 20, 30, doesn't matter. You can judge it based on how fast your machine is. Calculate the autocorrelation function for those, okay? And calculate the silo level. That has to be done automatically by the machine. So the silo level, you can choose either the maximum value of the silo level or the average value. Okay. And then select the PRBS that has the lowest SLL. So this would become some sort of code that allows you to select the PRBS, okay, that is optimal. Because this generator generates the longest one, right, with that shift register. So it will be X amount of values. And then you don't know if the first one is generated will be good, or the second one or the third. So maybe you generate, say, 100, and automatically choose the best. And that could be the one that you're implementing already, right? So as a deliverable, I will ask for a small technical report that summarizes your work, and a MATLAB code for me to check that it works. It's not that hard, is it? Should be alright. It's not that hard to formulate the problem.
Yes, yes.
Multi-look technique, okay. You remember the multi-look technique, that's to get rid of a speckle, okay? This is interesting, because now what I'm asking you to do is to take the MATLAB simulator that I've given to you, right? Remember I generated 5 scatterers, all separated from each other. So, how do you now emulate a case of salt and pepper type of image? Well, the salt and pepper phenomenon appears when you have multiple scatterers in the same resolution set. And this one contribute, each one with its own phase and amplitude. And depending on how the way you look at it, the angle under which you look at it, then this combination changes, okay? So how do you create a salt and pepper? Is that now, for each resolution cell, you don't put just one scatter, you put several of those, okay? So you'll start creating a very high number of scatterers across, okay? So that you have many scatterers within each resolution cell. If you do that, and if you make sure that the average energy per resolution cell is pretty much the same, you're now simulating a homogeneous area that in terms of energy produces exactly the same level, but because of the way they combine, you see these ups and downs that give you this salt and pepper look. Right? So first thing, generate your profile, your image will be just a profile, and check that you get these variations. Okay? Then how do you implement multi-look? You implement it by creating sub-apertures. So say on length, n samples, maybe there are 1,000 samples, okay? Maybe you create 4 sub-apertures of 250 each, and for each of those you form an image. And then you add up these images. And that creates your multi-look. The test that you're requested to do would be compare the results between the multi-look and the single look. So the one that you obtain with all the samples and the one that you obtain with multi-look. And show what? That the resolution of the multi-look is decreased by a factor equal to n being the number of sub-apertures. But also show that the salt and pepper effect is strongly reduced. Okay? That's one thing. Deliverable, there will be a technical report and MATLAB code. So that's the second assignment.
With showing that the resolution is decreased depending on the salt and pepper used visually or by...
Yeah, it will be visual. So create a scenario where you have a number of, say, scatterers that are composed of several scatterers each other. And then you see, you put them at a certain distance, so a group of scatterers here. Let me use a barboard to give you, to make sure you understand. So say this is your cross-range direction, right? So you choose only one range cell. And you know, the one that I simulated, I had a scatterer here, scatterer here, scatterer here, one here, maybe one here. Now what I'm asking you to do is, okay, put a lot of scatterers here. And then another group here. Make sure that the energy of this, so the sum of all the scatterers here, of this and all the others are similar. This creates a homogeneous type of scenario, right? Because the energy is the same. So I'm looking at a field. I wouldn't expect that that particular patch of the field is different in terms of energy. But when I look at the SAR image, they look very different. So if you do this, so that the energy here and the energy here and the energy here are similar or same even, right? Then when you form the image here, you should be seeing like this having quite a lot of variations. And you create a number of those, eh? You can generate it easily with MATLAB, just random and constrain the sum. Once you've done that, you form an image, and you should be able to see variations here, which are typical of salt and pepper. Right. That's the first part when you generate your scene. You generate your target and you generate your image. Once you generate this target, the image comes for free because I've already implemented the processing for you. So the processor doesn't change in the first case. The multi-look changes because now with the multi-look, what you do, you got all your samples here, right? And you divide them up like this. So let's say 1, 2, 3, 4, 5 sub-apertures. So now you form your image by using only this. And that's easy to do because in the simulator that I created, I got the antenna pattern, right? You just decrease that. Actually, don't decrease that, but you just sub-select some of the elements. Right? So that's what you're supposed to do. So you form an image with this, an image with that, an image with that, an image with that, and one with that. These images will have all a resolution that is 1/5 of the original resolution. So that's the first effect. But when you add them all up coherently, then you get your multi-look. That should give you the final result that you have to compare against this. So that's pretty much it. The deliverables are the same thing. Then we got another assignment. It's about ISO signal generation. So what I'm asking here is that you modify the simulator that you've got, the ISO simulator, by generating multiple nodes, multiple radars, so that at the same time, the same geometry, they're able to collect signal from different perspectives and form, instead of one image, form a number of images. So basically, you integrate new code that is able to modify that. And then as a test you have to, and simultaneously present the images. You know, if you go 4, then you present 4 images right away and say this is radar number 1, number 2, number 3, number 4. It'd be nice if you can also show the geometry where the radars are and where the target is. But that's something that just helps also you understand if you've done things correctly. And the interesting thing here, because this would be possibly too easy, the interesting thing here is that, okay, how can I, given the type of motion, how can I predict the position of the radar that provides a side view, a top view, or a front view? So, can I, based on the motions that I implement at that particular time, so I basically what you have to do, you have to, at that particular time, find the rotation vector. Once you found the rotation vector that depends entirely on the target, not the effective one, just the rotation vector. Well, given that, what's the position of the radar? Okay, that will give me a front view, a side view, or a top view. Okay. And as a deliverable, again, technical report and a manual code. The last one is the implementation of a PGA, phase gradient autofocus. Right? I gave you some hints how it works, but the idea now is to implement it. So implement the first step, which is a rough range alignment via constellation, and a second step using the maximum likelihood estimator. You've got a solution, you don't have to derive it. The solution is already there. Test, okay, use MATLAB code provided to generate targets. Generate a target with at least 15 scatterers. Choose some target that you can recognize, like a ship light or an aircraft light or something like that. And then once you have produced this code, the PGA, compare PGA and ICBA. CBA is already implemented, it's the one that is already running. PGA is not there, must be implemented. And then compare images. See if they work well or not. And again, technical report and MATLAB code. Yes.
Yeah, can we at least have a day or two to gauge the difficulty of these problems? Because since the SAR thing has been a day or two since we last did them, can't gauge exactly which one would be more difficult to do. So, is it possible to we don't have to choose now.
No.
Oh, hey, because I thought you wanted us to choose now.
No, I took this time to explain.
I was like, ish, no, we need some time to gauge which one is more difficult.
No way. No. Look, it's entirely up to you. You can even don't show up to me, don't tell me anything, and the deadline you give the work. I don't need to know.
Okay.
Well, if you want to discuss it with me in the next few weeks, then of course you will have to choose it and start working on it. No, of course not. Now think about it and see what's the most interesting for you and the most doable given your skills and your. They all require a bit of work, but being nearly full masters engineers, you need to be able to solve these problems. I mean, some of you already work in companies and you know that you have to solve problems like this. So it's something that requires a bit of thinking and a bit of work. It's not just calculate. Yes.
How detailed do you like your technical reports to be?
That's up to you. As long as it's clear. I don't want it too long, for sure. Be concise as a gift, use it. Yes. Just send me PDF, generate whatever it is, lucky, whatever it is. Doesn't matter. And in terms of, any format in terms of the structure of the technical report, an introduction, and the methodology you used, how you did things. The MATLAB code is the most important thing because that shows that you've done the job and it works. If you're good at explaining things, of course, that's very much appreciated. Think of this as a, you know, a classical case that your boss at work gives you this job and say, okay, do it and bring me a technical report so that I understand how you did it. Take it as that challenge, right? Cool. Yeah, well, you can write emails to me, ask me for details that you haven't understood. You don't have to digest it all now. But then we can use those, you know, tutorial time to discuss. We can have one-to-one discussion regarding this assignments here. Okay. Before lunch, okay, what I want to give you now is this. I'm not going to go through the solution because I can give you a solution PDF. But if you want, you can use this one as a first exam-like type of problem. Right? Then I will give you all the past exams unless they're already online and you can already access them. And the solution. So first try to solve it, don't look at the solution until the very end. Otherwise, these are typical things that can appear for your exam, and they require, of course, you to know about the problem, about the system, about how it works, and then some calculations that, of course, yeah, well, you can use formulas, yes.
Can we bring in the formula sheet?
Yeah, absolutely.
So we bring in the, or are you going to provide the formula sheet for us?
Well, for this, I mean, trigonometry, you know, sine of this, cosine, I don't know what you need. I think any formula handbook can help. Yes.
Will you also provide the astrophysics equations when you turn your orbits?
What? You don't need to determine the orbit because if you read this, well, it tells you that
Okay, I see now.
it's approximated as a linear.
Okay, cool.
Now, of course, I will ask you to do
That you just know offhand.
Not the same.
there's simple things that then you look at solution is simple, but they require a bit of knowledge of how to calculate angles, velocities, which you have to do.
Good derivation.
Yeah. You know how to calculate the effective rotation vector known in the geometry. Yes. It is a matter of angles and distances, and then there's a cross-range resolution. You know the formula. You know which parameters are in there. Transmitted waveform bandwidth that you need to obtain that resolution. Well, C over 2B. And then this problem here concerns the ambiguity, remember? So I give you the size of the satellite and I say, okay, you have to define the window that contains it. And that depends on a number of parameters and so on. You will always have formulas with you in your life. It's not an issue. The problem is what to use, how to use it. So those are the problems you have to solve. Nobody will ask you to remember all the possible formulas. There will be some they will use continuously and it will remember automatically. So, I think that's us to. Yes, we're done. Eh? We're finished. So just,
Can you get somebody to take a picture?
Beautiful.